Hello everyone, let's now move on to look at section 3, further equilibrium problems. So in the previous chapter, we have met the idea of equilibrium, where all the forces on an object balance. When the object is in contact with the surface, you need to now include a normal reaction force in the calculations. We have introduced the normal reaction force in our last video. So let's have a look at this example. Okay, so in this question, it says a box of mass 16 kilogram rests on the smooth horizontal table. 4 light inextensible strings are attached to the box. The tensions in the strings are 12 Newton, 23 Newton, 18 newtons, and T newtons, as shown in the diagram. Okay, given that the box is in equilibrium, find part A, the value of T, and then the magnitude of the normal reaction force between the box and the table. Right. So now here on this diagram, we've only been given the 4 tensions. However, let's think what other forces are acting on the object that's not been drawn on the diagram. So firstly, you can see that the box has a mass of 16 kilogram, which means there will be the weight acting directly downwards, and the weight equals to mg, so that will equals to 16g. Now, if there is a weight, the box is resting on the surface, that means there must be a normal reaction force acting perpendicular to the surface. But we don't know what's the normal reaction in this case yet. We will find out later. Okay, so far we have now added in all the forces acting on the box. Let's start to think about the question. Now, the box is in equilibrium, which means the forces should balance in each direction. If we're going to find out the value of T, so T is a tension in the horizontal direction. So the box is in equilibrium, that means the forces in the horizontal direction should balance. So here we have 23 newtons acting towards the left-hand side. And here on the right-hand side, we have 18 newton and 10 newton. So that means all the forces acting on the right-hand side should balance with the forces acting towards the left-hand side. So part A, we now know that 23 must equals to 18 plus T. So that means T must equals to 5 Newton. And that's it. Okay, so let's look at part B. Right, so we're looking for the magnitude of the normal reaction force between the box and the table. So that means we have to consider all the forces acting in the vertical direction. Again, we have 3 forces. 2 forces acting upwards, which are the normal reaction force and the 12 Newton. We have 1 force acting downwards, which is the weight. So those 3 forces should balance. So that means the normal reaction force R plus 12 Newton must equals to the forces acting downwards, which is the weight. So that equals to W. So that means R plus 12 must equals to, we already know that the weight is 16g, so let's replace that. So now we get R equals to 16g minus 12, and we know that G is 9.8, so you can put into your calculator and work out the value of R, which should come out to be 145 Newton. So this is your normal reaction force. Okay, so hopefully so far so good. Now let's have a look at another example. Okay, so the normal reaction force only acts as long as the object is in contact with the surface. When there is another force pulling the object away from the surface, the normal reaction force will decrease. If it reaches zero, then the object is no longer in contact with the surface. Okay, so you might want to make a note here. If the object is no longer in contact with the surface, that means we don't have a normal reaction force anymore. So let's have a look at this example. Okay, so here it says a book of mass 320 grams rests on a horizontal table. A girl pushes vertically down on the book with a force of 8.2 Newton. The book is attached to a light, inaccessible string, and the boy pulls the string vertically upwards so that the tension in the string is T Newton. A expresses the normal reaction force in terms of T, and then find the smallest value of T required to lift the book off the table, and then find the acceleration. Okay, so again, in this question, we should start by drawing a diagram and label all the forces acting on the diagram. Right, so let's say this is my book. Okay, so what also do we have? So we know that the book is resting on a horizontal table. So let's draw a straight line to represent the table. Let's say this is the table. Okay, so what force do we have acting on this book? Well, firstly, we know that there will be a weight. So W equals to mg, and the mass of the book is 320 grams, so that means weight equals to 0.32 g. Remember what we said before, when we're talking about the weight, mass has to be in kilogram. That's why I will change 320 into 0.32. Okay, so what else is acting on the book? Well, because the book is resting on a table, that means there will be a normal reaction force, which is R. Unfortunately, we don't know what R is at this moment. Now let's have a look what else is acting on the book. In the question, it says a girl pushes vertically down on the book with a force of 8.2 Newton. So let's say we have a force pushing downwards, and that's 8.2 Newton. And then it says the book is attached to a light inaccessible string, and the boy pulls the string vertically upwards with tension of T Newton. So let's go over here, and we have a force of T going upwards. Right, I think that's it. They are all the four forces acting on the book. Okay, so part A, we're looking for the normal reaction force, and we are going to express it in terms of T now. So you can see that the book is now resting on the table and it's not moving, so that means all the forces are in equilibrium, so they all balance out. So that means the forces going upwards should balance out with the forces going downwards. So part A, here. Okay, so forces going upwards would be the normal reaction force R, and the tension going upwards balance with the force acting downwards, which is 8.2, and the weight, which is 0.32 g. So now we can write that R equals to 8.2 plus 0.32 g, take away T. We can also replace G with 9.8 to get R equals to 8.2 plus 3.32 11.136 minus t. So that means R equals to 11.336 minus t. Okay, so that's our answer for part A. Now let's look at part B. Find the smallest value of t required to lift the book off the table. So now, if the book is being lifted off the table, so at that moment, there will be no normal reaction force. So that means the R should equals to 0. So when R equals to 0, we would get 0 equals 2. So use this equation here. 11.336 minus t. So that means t would have to equal to 11.336 Newton. Okay, so that would be the smallest value of t. Right, part C. Let's find the acceleration of the book when tension T equals to 12 Newton. Okay, so you can see that when the tension is 11.336, the book will start to be lifted off the table. So when T is greater than 11.336, that means the book will be away from the table. So the book is not resting on the table anymore. That means there's no normal reaction force at all. Okay, so that means, well, we have to reconsider the diagram again. So let's draw another diagram. Maybe I'll use a different color. Let's use red. So this time, on the book, there will only be the weight, which is 0.32 G, and we still have the force 8.2 being pushed down by the girl, and we'll have the tension T and in part C given T as 12 Newton. So that's it. So now, because the tension is greater, that means the book will be lifted up. That means there will be an acceleration and that will be going upwards. So let's say going up is our positive direction. So now we actually have to use F equals ma. So in this formula, let's think what's my resultant force. So if going up is positive direction, that means T would be positive. So we will have 12 Newton and the 8.2 and the weight are going downwards, which is against the direction. So that means they will both be negative. So we have to do 12, take away 8.2, take away the weight, which is 0.32 G. And that will equals to MA. M is 0.32, and then times by A. So we'll get 0.664 equals to 0.32A. So that means A will equal to 2.08 meter per second squared. Okay. Right. So hopefully you're okay with this question. Now let's look at one more question. Right. Oops, sorry. Okay, now I don't know if you remember from our previous video about the normal reaction force. Now, the normal reaction force does not need to act in a vertical direction, okay, but it is always perpendicular to the contact force and acting away from it. So let's have a look in this example where the normal reaction force is not vertically upwards. Right, so Here, in this example, a box of mass 1.2 kg is pushed against a rough vertical wall with a force of 40 Newton and rests in equilibrium. Find the normal reaction force between the box and the wall, and then the magnitude and direction of the frictional force between the box and the wall. So here is the diagram. A box is being pushed against a wall, and the force 40 Newton is being applied to the box, and because it's pushed onto the wall, hence the direction is to the right hand side. Now, because the box is in contact with the surface, which is the wall, so that means the normal reaction has goes perpendicular to the wall this time, hence the normal reaction will be towards the left hand side. Okay, and we have the weight acting downwards, and because the box is not moving down, that means there must be a frictional force stopping the box moving down, hence the frictional force will have to go upwards. Right. So hopefully you have now understand how those four forces acting on the box. Now let's look at question part A. So let's work out the normal reaction force between the box and the wall. Well, you can see the normal reaction is actually acting in the horizontal direction this time, so we only need to consider the horizontal force. And in this case, there's only one other force, which is the 40 Newton. And because the box is in equilibrium, so those two forces must balance. So straight away, we now know that the normal reaction force has equals to 40 Newton. Okay, part B. The magnitude direction of the frictional force. So the frictional force is acting in the vertical direction. So we only need to consider the forces acting in a vertical direction. And in the vertical direction, we have the frictional force and the weight. And that's it. So again, because the box is in equilibrium, so the frictional force has balance with the weight. So we now know that F must equals to 1.2 G, and change G to be 11.8. We'll get the frictional force F equals to 11.8 Newton, and it has to go upwards. Okay. Right, so I hope you find those examples all right, and they're not as difficult. So now you should try some exercise. Here are the questions for exercise 12-2C, question 1 and 2. When you do those questions, again, please remember to draw a diagram and label all the forces acting on the diagram. Here, question 3 and question 4. Question 5 and question 6. Question 7. And the last one, question 8. And when you do question 8, just be careful with the tension is in vector form. So you have to consider all your forces in the vertical and the horizontal direction separately here. And here are the answers to the exercise.